In section 4.7, we're going to talk about change of basis. Now, the idea behind a change of basis is that we can have lots of bases for a particular vector space. But whenever we choose a specific basis and we have a finite dimensional vector space, I didn't write finite dimensional, but when we have a finite dimensional vector space, there's this coordinate mapping that we've seen that maps onto Rn for some value of n. And this provides a coordinate system for our vector space. So here's what I mean by that. Let's assume I have a vector and it can be written as a linear combination of basis elements B1 through BP. The coordinate vector of V relative to basis B is the vector of those coefficients. So we call those coefficients the weights sometimes, but we know the coordinate vector. We've seen that before. Now we know that there's lots of different bases for any one subspace, or excuse me, for any one vector space. All right, so there's a lot of different ways we can write the coordinate vector if we are allowed to use different bases. So what we're going to do is we're going to sort of jump back and forth between a basis one, number one, and basis number two. And you might say, well, why is there impetus to use different bases? And the two big ones are first being able to translate and communicate between people using different systems. So if I'm using a certain system and you're using a certain different system, then we can sort of go back and forth. I can do some work in my system. I can send it to you. You can translate it. You can do some work in your system, send it back to me, and we can go back and forth with translations. All right, think about speaking in different languages, if you will. All right, being able to translate and communicate effectively between people who are using different systems. The other reason we'll use different bases, we'll see in the next chapter, and that is that certain transformations are going to look a lot nicer with a particular basis. So we're going to choose sort of a nice basis in the next chapter, and you'll see how to do that so that the transformations we're going to deal with are easily calculated, easily dealt with. All right. So we've dealt with this before. Think about a vector x, which we will call from R2 is 2, 1. And now we're going to use the basis 4, negative 1, 2, 1 as the basis I want to utilize. The basis coordinate vector for x is the vector 0, 1. Basically what this means is we took 0 times 4, negative 1 plus 1 times 2, 1 and got back the vector x. This is what I mean here. So 0 times 4, negative 1 plus 1 times 2, 1 is equal to 2, 1. Now that's a vector equation. We've seen also that if we wanted to translate that into a matrix equation, what we would have done is we would have taken, excuse me, this will take a second to write out, the matrix for negative 1 first column, 2, 1 second column, times the coordinate vector 0, 1 is equal to the vector 2, 1. So as a matrix equation, it looks like this. Again, we call this the basis matrix, P sub B times X sub B equals my X vector. Okay? So that's the idea. So let's try to think about how would we translate between a basis into another basis. So let's say we have this basis here, which is B1, B2, and another basis, which is C1, C2, and we have this relationship between them. These equations, B1 equals 2C1 plus C2, and B2 is equal to negative 1C1 plus 4C2. We're going to let V be written with respect to basis B, and we want to rewrite V with respect to basis C. So in other words, we want to figure out a linear combination of basis elements from C that could work. Now, all we really have to do is say, well, we know that our vector V is 5 times B1 plus 3 times B2. Let's cut and copy that. And so what we're going to do is we're going to replace B1 with how to write it in C2. And we're going to replace B2 with how we write it in the basis C. All right, so replace B1 with how you write B1 in basis C, and write B2 with how you write basis 2 in basis C. I misspoke there. Okay, so we write B1 as the linear combination of basis elements from basis C, and we replace B2 with the linear combination of basis elements from basis C. There we go. And then all we're going to have to do is distribute, combine like terms, and we'll have what we want. So let's do that real quick. I'm not going to belabor the point. So 5 times 2 is 10C1 minus 3 times C1 gives me a 7C1. 5 times C2 plus 12 times C2 gives me a 17C2. So there we go. That's how we would write the vector as a linear combination of basis elements from C. Now the nice thing about this is once you see that, we can translate all of this stuff into coordinate vectors. Because remember, a coordinate vector is just the coefficients of the basis elements from whatever basis I'm dealing with. So we can translate that all into coordinate vectors, and we could pose the question this way. If I have two bases, B and C, and I know that the basis elements from B can be written as this and that, and I know that there's a vector V out there whose coordinate vector with respect to basis B is 5, 3. Could we find the coordinate vector with respect to basis C? Now, if you think about this, this is the exact same problem that we just did. We had in our previous slide, our vector was 5 times B1 plus 3 times B2, and we had these two identities. So we have the same two identities, and we have this same vector v, which is 5 times b1 plus 3 times b2. Now the nice thing about this is that when we translate it into an equation for R2, I can think of this as going from a vector in R2 to a different vector in R2. So hopefully that makes sense. We're going to go from basis B, this coordinate vector, and we're going to try to create a coordinate vector there. Now, if I think about this, we're going to go from this coordinate vector using this basis B to this coordinate vector using this basis C. What it's going to turn out to be is a matrix transformation. And in fact, hopefully we can see this, that what we're going to do, I claim, is that we're going to take a 2 by 2 matrix, we're going to multiply it by 5, 3, and we're going to get out a vector with respect to C, a coordinate vector with respect to basis C. Now, if you think about what those coefficients had to do from before, well, 2 times C1 plus 1 times C2, I got to multiply that times, take, let me reset. I would have had to multiply the 5 times this, and then add the 3 times this. Now, if you think about what that means, it means that 2, 1 should be the first column of that 2 by 2 matrix, and -1, 4 needs to be the second column of that 2 by 2 matrix. And so 2, -1, 1, 4, let's test this. 2 times 5 plus -1 times 3 gives, in fact, gives me 7. So let's insert an actual vector here. So 2 times 5 plus -1 times 3. All that turns out to be just 7. 1 times 5 plus 4 times 3 gives me 17. So notice that this matrix translates from basis B to basis C. And all I had to do was write the elements of B with respect to the matrix, the basis C. All right, all I had to do was make these columns my basis elements in B written in terms of C. Okay, so in other words, the columns here, this 2, 1, let me write this down here. So 2, 1 is simply my basis element B1 written with respect to basis C. That's what I'm trying to say. Okay. And -1, 4 is just B2 written with respect to basis C. Okay. So that's where these columns came out of. So there you go. We have this nice matrix that will change every B coordinate vector to a C coordinate vector. So I want you to use this matrix to figure out if you started with a B coordinate vector of 6, -7, what would a C coordinate vector be? We're using the same bases B and C. So go ahead, push pause on the video and try that. All right, hopefully you did that. All we have to do here is say we want to go from B to C again. So we start with the B coordinate vector, 6, -7. And if we're going this way, all we have to do is multiply. So 2 times 6 is 12, plus -1 times -7 is a +7. That gives us a 19. Then we're going to take 1 times 6 is 6, plus 4 times -7, -28. And when we combine those, we get -22. And there we go. So that is the vector v with respect to basis C. All right, 19, -22. That's the coordinate vector of v with respect to basis C. Now notice that in these two examples, I didn't even have what the actual bases were. I just had the fact of that basis B can be written this way, and B1 can be written in this way, B2 can be written in this way. Okay? So all we did there was use that what we call a change of basis matrix. All right? We used a change of basis matrix. And in general, we can always do this. Now I kind of wrote this backwards. I wrote matrix times element in basis B is equal to element in basis C here. But this is exactly what we did here before. I say backwards. All I mean is that I've been writing the vector with respect to basis C on the right instead of the left. Okay, but there you go. By the way, this is the notation they use. If I use a change of basis matrix, we call that P. We write B on the right and then an arrow to C on the left. Okay, so we change it from B to C. Now there's a reason for that. That's because if you wanted to do a lot of change of basis matrix, you start on the right, your vector, and then you multiply it, and then you multiply by another matrix, and then another and another, and keep going. So there you go. And it's nice to find this change of basis matrix. All we have to do, if we're going from B to C, is write the elements of the bases as column vectors written with respect to basis C. Okay, so just like we saw earlier, that the columns are basis elements from B written with respect to basis C. So what I would like you to do is now try one on your own. I want you to come up with a matrix which transforms from vectors coordinate vectors written with respect to basis A into coordinate vectors written with respect to basis B. So we're going to go from A to B here. So create that matrix, if you will. Push pause on the video. All right, so hopefully you did that. We have these three equations here. A1 is 2 times B1 plus 4 times B3. A2 is negative 1B1 plus 5B2 plus 6B3. And A3 is B2 plus 4B3. And we want to take vectors written from A and translate them into vectors written with respect to basis B. So all we have to do is write each vector in A. What is as a linear combination of vectors from B, and then we write the coordinate vector for A1 in column 1, so that would be 2, 0, 4. The coordinate vector for A2 in column 2, that's negative 1, 5, 6. And the coordinate vector for A3, which is 0, 1, 4, we write in for column 3. Now, the one thing you have to be a little bit careful of is that which direction we are going. So this matrix takes a vector from A into a vector from B. And the way you test that is you say, well, what would the coordinate vector with respect to A be for A1? Well, with respect to A, the coordinate vector would have been, the vector, if you think about this, 1, 0, 0. So that is the coordinate vector. I'm going to do a little bit of bad notation, but that's the coordinate vector with respect to A. And notice what that would do. That would give us out 2, 0, 4. And that's my A1 written with respect to basis B. Okay, so with respect to basis B, 2, 0, 4. All right, so that's a good check that we did write it going the correct direction. Again, we go from A to B. So start with A, multiply times A, get to B. All right, so that takes my vectors from coordinate vectors written with respect to basis A and translates them to coordinate vectors written with respect to basis B. All right, now once we have that, we can use it. We can take a vector and say that vector x can be written with respect to basis A as 4, negative 1, 7. So this would be like we have the vector x is a linear combination of 4 times A1 minus 1 times A2 plus 7 times A3. And we want to translate that into a coordinate vector with respect to basis B. Try to figure out how you would do that using the matrix we had from the previous problem. Go ahead and push pause on the video. Okay, so we're going to try this. So we take this matrix that takes a vector with respect to basis A and translate it to a vector with respect to basis B. So all we have to do is say, well, our 4, negative 1, 7, that was with respect to basis A. we want a vector with respect to basis B. Again, I'm kind of abusing the notation here, but lets me keep track of what's happening. So if I take this matrix and I simply multiply this matrix times a vector written with respect to basis A, then my coordinate vector written with respect to basis B is going to be my result. So in this case, what that would be, well, we can just multiply this. 2 times 4 is going to be 8. Minus 1 times negative 1, that's going to be a plus 1. And 0 times 7 is a plus 0. So that first entry into this vector is going to be, again, 2 times 4, negative 1 times negative 1, 0 times 7. First entry is going to be 9. Second entry, 0 times 4, plus 5 times negative 1, plus 1 times 7. All right, so that second entry is going to be a 2. And then lastly, 4 times 4 is 16. 6 times negative 1 is a minus 6. 4 times 7 is plus 28. And so what we get is the vector written with respect to basis B will be 9, 2, 38. Okay, so that's again, I'm abusing notation a little bit, but that's the vector written with respect to basis B. By the way, this is a common abuse of notation. Basically, what we mean by that notation is that the vector x that I had written with respect to basis B has to be this 3 by 1 vector. All right. So the proper way of writing it is 9 to 38 is that way. The x written with respect to basis B is 9 to 38. All right. So I want you to go ahead and do another one. I want you to take a vector written with respect to basis A, which is 2, 0, 5, and come up with the vector written with respect to basis B. Push pause on the video and go ahead and do that. So in this case, all we have to do is change our vector here from what we had before to the vector 205. By the way, so we're going to multiply that and get something written with respect to basis B. By the way, if you want to, all you really need to do is multiply this in your calculator. So we plug in this matrix into our calculator as sum matrix. Doesn't matter what we call it. This 205 we'll put in as a different matrix, and then we'll multiply those two. All right? So let me hit our calculator up right now. So here we go. I have this already input in my calculator. Now I chose the letter D. I chose matrix D to put in my change of basis matrix that goes from A to B. And then I used matrix A to be this vector 205. So all we have to do is go to matrix D, which is my fourth matrix there, and then multiply it times my matrix A, and I get 4, 5, 28. So written with respect to basis B, we get 4, 5, 28. By the way, you can check that on your own if you'd like to. 2 times 2 minus 1 times 0, 0 times 5, that does give you 4. 0 times 2, 5 times 0, 1 times 5, that gives you 5. 4 times 2, 6 times 0, 4 times 5, that gives you 28. So you can do that by hand too. Either way, what we get is that the vector that I was looking for, written with respect to matrix B, is 4, 5, 28. Okay, so there we go. Now, what's going to happen if we want to go the other way? All right, so we found this matrix P, which takes me from A to B. What if I wanted to go from B to A? Well, it's a pretty straightforward observation that if we have a matrix, whoops, that takes us from A to B, in other words, we have a matrix P, which when I multiply it times a vector written with respect to basis A, I get out a vector written with respect to basis B. All right, so if I have a matrix doing that. So pretty obvious that if I want to go from B to A, there's a couple of ways. I could row reduce and solve the equation. A little bit faster method, however, is just to multiply times P inverse on both sides. Now, it turns out for every change of basis matrix, it will be invertible because we go from basis to basis. So going from basis to basis, we have to have invertible matrices. So all you have to do is use P inverse to go from B to A. So why don't you go ahead and try that. Instead of writing a vector with respect to A to start out with, I want you to come up with the vector written with respect to A if your vector written with respect to B is a 4, -1, 7. So all we have to do is we have to use this matrix equation, my P that I found earlier, the same one that I've been using here, the P that goes from A to B, which is this 3 by 3 matrix. All I have to do is take that P, take the inverse of it. I'm going to actually just make sure we see that. It's the inverse of the P we were dealing with earlier. What that would do, inversing, is going to go from B to A. So we start with B, want to go with A, use P inverse. Now what I'm going to do is I'm going to use my calculator to do that. So I've already have my matrix B, which is my vector that I'm using here, 4, -1, 7. You saw earlier that I already had my D in there as the matrix. So all we have to do is go to matrix D, that's 4. We're going to do the inverse of that times matrix B, which is 2. And there you go. 1.875, -0.25, and 0.25. Okay, so 1.875, -0.25, and 0.25. So our final answer there is that the vector x written with respect to basis A is 1.875, -0.25, and a positive 0.25. Okay? Now what I'd like you to do is I would like you to do this problem on your own using that same change of basis matrix from A to B. All right, make sure you push pause if you haven't yet, because we're going to move on. We're going to say, well, now all we're changing is that we wanted to use 2, 0, 5. Obviously, we're not going to get that. We're going to get some other 3x1 vector. We take our matrix inverse. So again, go back to matrix. Which one was that? 4. Inverse. And if you remember way back up here, we already had 205. That was in my matrix A. So we're going to take the matrix inverse times matrix A. I think that'll do it. And there you go. I'm going to turn that into a fraction just so it's a little bit easier to see. There you go. 23 over 24, 1/12, 5/12. It should be negative 1/12 and then 5/12. So there you go. 23 over 24, negative 1/12, and then 5/12. Okay. So that is the matrix that we're looking for. Or excuse me, the vector, which is obviously a matrix that we're looking for. Okay. So there we go. Now this is really nice because it was really easy to find the matrix P that transforms from A into B because we had these lists of identities, right? We had A written with respect to B, each element of A, I should say, written with respect to B. But what if we don't? What if instead we just have an explicit definition of our vectors? So for instance, what if A consists of 2 vectors and they could be anything, and B consists of 2 other vectors and they could be anything? Well, can we change back and forth easily? And the answer is yes. So hopefully you understand what I mean by an explicit definition of the vectors. What I mean by that is we're going to have some, instead of writing A is a combinations of B, we're going to say, well, what if my element A1, let's actually go to a 2x2 example. Let's get out of the 3x3. What if A1 was the vector 3, 4, and what if A2 was the vector -2, 1? You know, something of that nature. Okay, so if we have if we have this basis for R2, and then we have another basis for R2, which again are just 2 different vectors, how can we translate from one basis to the other without having to do all of the work of rewriting a one basis as a coordinate matrix in the form of another? Well, this is a spot where we use what we learned before. Remember what we did before. We had this change of coordinate matrix, P sub B. And what that was were just columns. The columns of that matrix were my basis elements, B1, B2, all the way to Bn. And what that did is it changed a coordinate vector written with respect to B into a vector in the standard basis. Okay? So this is a vector. A normal vector is written with respect to the standard basis. So we could do that for B and then take it into the standard basis. And we could have also done that for basis A. So the way to do this, if we have explicitly defined vectors, is to realize that we could have done this. We could have taken my change of coordinate matrix for basis B, gone into the standard basis, and my change of coordinate matrix for basis A, and gone into the standard basis. Now notice that this is the same x in either case. This is the same vector x. And so what we have here, we can substitute this x for this product, or substitute this x for this product. And what we can see is that we can go from change of basis, we can change the bases from A to B or from B to A using this equation. And we already saw that since A and since B are bases, these will be invertible. So if we want to go from A to B, all we have to do is move the change of coordinate matrix PB over here with an inverse. If I want to go from B to A, all I have to do is move the change of coordinate matrix over here with an inverse. So that's it. So if you want to go from B to A, you go from B to A, do basis with respect to B matrix, and then the inverse of with respect to A matrix. If you want to go from A to B, change of coordinates with respect to A matrix times change of coordinate with respect to B inverse matrix. So let's do an example here. Let's take, and we have two explicitly defined bases for R2. And we're going to find the change of basis matrix that goes from A to B and the change of basis matrix that goes from B to A. By the way, these are going to be inverses of one another, so hopefully that'll all make sense. So I want you to push pause, refer to the last slide, and try to do this. All right, so hopefully you went ahead and did that. Now we start out by just noting that my basis that changes from A into the standard basis is going to be P of A. Here with columns 4, 1 and 10, 3. My change of basis matrix that goes from B to the standard basis is going to be 1, 1, 2, 1. And so basically, which way do we want to go? Do we want to go from, let's go from, B, no, let's go from A to B first. Okay. By the way, I gotta figure these things out. If you remember what that did, what we would have to do is we'd have to start at A. So we're going to start at A, and then we're going to multiply by the inverse of starting at B. Okay, that's better. Okay, start at A, could be. By the way, this is why this little arrow is always pointing from right to left. Okay, you go from A 2b. All right. Now what I'm going to do is I'm just going to utilize my calculator for that. I'm going to put in this matrix here into the A matrix of my calculator. I'm going to put in this matrix into the B matrix of my calculator, and then let my calculator do all the hard calculations, like finding the inverse and then multiplying. Okay, so let's go ahead and do that. So by the way, I already did that. I forgot to mention that. So I said it like I hadn't done it. So there's matrix A, there's matrix B, okay? And so what we would do is we would take matrix B, write that one first, do the inverse of that, and then times matrix A, and there you go. Now we go from A to B. All right, so when you did that, we got -2, -4, 3, 7. So that's what we do, -2, -4, 3, 7. Whoops. All right. And by the way, if we want to go the opposite way, pretty straightforward. Going the opposite way, we just go matrix A, inverse, times matrix B, hit enter, and that goes from B to A. So there we go. So here it is. So going from B to A, -3.5, -2, 1.51. Going from A to B, -2, -4, 3, 7. Okay. By the way, what I memorize, I don't try to memorize this necessarily. What I like to memorize is this equation here. Oops. Well, no, I screwed that up. This equation here. Take matrix of basis A times a vector written with respect to basis A is equal to matrix of basis B written with, times vector written with respect to basis B. Okay, that's kind of the thing I memorize. And then I just say, okay, if I want to go from A to B, just move that one over with an inverse. If I want to go from B to A, I move this one over with an inverse. All right. So now that we've done that, and by the way, let me just say one last thing here. These two matrices, if I've done them right, they should be inverses of each other. Okay? So what I could do to check that, let's say I wanted to, oops, let me go this way. Let's say I wanted to do, check if that was an inverse. So let me take this matrix. And then see if this will do it. See if just taking the inverse of that matrix. So I take this matrix here that I just found, inverse of that, see if in fact I do get -2, -4, 3, 7. And yes, I do. So again, these two matrices should be inverses of each other because obviously one takes us from A to B and the other takes us from B to A. And there we go. Now, once we've found these, then we can use them to solve problems. We can say, for instance, let's find a vector written with respect to basis A if that vector written with respect to basis B is 3, negative 1. And do the exact same with the opposite. If a vector is written with respect to basis A as 3, negative 1, what would the vector be written with respect to basis B? Go and push pause on the video and then solve those questions. All right, so let's go through this. So first off, I want to go from B to A. And again, I'm using the matrices that I had in my last, or excuse me, in this problem, right? So I'm using this A and this B. And so once I've already found the change of basis matrix from B to A, and once I've found from A to B, then I can just take 3, negative 1 times each thing. And you know what? I think when I did this on my own, I used a positive 1. So I did 3, positive 1. Dang it. So I'll have to do some adjusting. But the first one, so I'm taking 3, negative 1 with respect to basis B. I'm going to multiply that times my matrix that I just found that translates from B to A. And this is where I just messed up the whole thing. That's fine. So negative 3.5 times 3 plus negative 2 times negative 1 gives me a negative 8.5 as my first entry. And then I'm going to take 1.5 times 3 plus 1 times negative 1. That'll give me a 3.5 as my second entry. Now what I'm doing here is I'm just writing these little subscripts so that I keep track of which one I'm writing it with respect to. I like to do that. Again, it's not perfect notation, but it does help a lot. And all that means is that this vector x written with respect to A is negative 8.5 and a positive 3.5. All right, so the coordinate vector for x with respect to basis A is negative 8.5 and 3.5. Now, if you do that the other way, if instead of going from B to A, you go from A to B, again, let's pretend I have a vector negative that's written with respect to A as 3, negative 1. I messed this up as well because I screwed up my positives and negatives. So what would that be? Negative 2 times 3 is negative 6. Negative 4 times negative 1 is a positive 4, so negative 6 plus 4 is negative 2. 3 times 3 is 9, plus 7 times negative 1, so 9 minus 7 is 2. So with respect to basis B, the vector we're given is negative 2, 2. All right? So there we go. All right? Now, I would like you to do the same idea here. Find the matrix which changes vectors with respect to B into vectors written with respect to A with this A and this B. Push pause on the video and go ahead and do that. So I've written down all this stuff. So again, we're going from B to A. So the way I do this is I write down my matrix, change of matrix matrix from A to the standard basis is going to be 2, 0, negative 3, 1. Change of matrix B into the standard basis is -2, -3, 5, 5. And so all I do is take A inverse times B, and this will take us from B into A. Okay, that's -1, -1.52, and then 0.5. That's what I got out on my calculator. Okay, hopefully I've typed everything in correctly. By the way, notice that if I find from B to A, I really don't actually need to find from A to B because going from A to B is simply doing B to A inverse. So if you ever need this, you can just take the inverse. And if you don't know yet on your calculator, so on your calculator, you can, if I have my matrix C as my change of basis matrix, and so I did A and B, and then I put it into C. If you want to find the inverse of that, we just hit the inverse button, obviously. But here's what I want to do. So let's say I have this matrix now. I don't want to use the inverse key. If I wanted to store this matrix in another place, I could put store right down here by the 1, and then go back into the matrix and say, I actually want that to be my new matrix D. So now my matrix D would do the reverse, okay? So of what I did. And that's how, by the way, I got the original matrix in matrix C as well. I just put A inverse times B, and then I hit the store matrix C. So there we go. All right, that is the matrix that goes from B to A. Now, once you have that, you can answer questions like this. Let's do the exact same thing. Let's go from B to A first, and then let's go from A to B, and we'll still use 3, -1 as our entries. So hopefully you went ahead and did that. So here we go. Let's start. Let's go from B to A first. So if I have 3, -1 written as coordinate vector with respect to basis B, I'm going to take my matrix that sends it from B to A, and I'm just going to simply multiply 3, -1 times that matrix. Now, I do want to say real quick that obviously the order is important and all that kind of good stuff. If I try to take 3, -1 and put the matrix on the right-hand side, wouldn't work so well, as we all should know. But when you multiply that, you end up -3 plus 1.5 gives you a -1.5 as the first entry, and 2 times 3 is 6, minus 0.5, that's a 5.5 as the second entry. Excuse me. So the matrix, or the vector, is -1.5 and 5.5. Okay? Now, I did this on my calculator, and I multiplied it using my calculator. If you want to do this by hand, you could do that. Obviously, I kind of talked through it by hand, but the real way I did it is on my calculator. And that'll be kind of important in the next problem. Once we go from A to B, 3, -1, and you're looking for the entries with respect to, well, we're looking for the coordinate vector of x with respect to basis B. So what I did on my calculator is I just took my matrix, which I have as my matrix C, and multiplied it times the matrix 3, negative 1. But, excuse me, let me say that again. I want to go from A to B this time. My B to A I have as stored as in matrix C. So I took C inverse, multiplied it times 3, negative 1. And what I came out with is a 0 and negative 2. All right, hopefully you got the same thing. So the coordinate vector with respect to basis B is 0, negative 2. All right, so that's what we have. Now, that shows you how to go from one basis to another, and that is how we are going to end chapter 4. Okay? In the next chapter, we're going to look at a lot of different stuff. We're going to see why, again, these transformations and things, why would we want to go from one basis to another? All right, we're going to look at that, not just communicating, but with transformations that are nice. All right, so this is the end of chapter 4, and we'll see you next time.